Welcome to Secure Software Development. We're going to start, as we usually start, by talking about the metaverse. Here we are in the museum of the metaverse, because the metaverse has been around so long now, it makes sense to have a museum of the metaverse. And what better place to put it than in the metaverse? And oh, wait, I don't mean this metaverse. I apologize. I get a little confused. I mean this metaverse, the universe of apps created by Meta. So there are a lot of them. This is a few of them. And of these apps, we really want to talk about one in particular, and that's this one down here at the bottom, WhatsApp. So you're probably familiar with WhatsApp and know a little bit about it and probably use it. And that's great. Just be aware that the last time I taught this class, back in 2022, this happened while I was teaching the class. Someone posted they were selling WhatsApp information online. It mainly consisted of phone numbers for users of the app. And you may think, I don't care. But, maybe you're right. But just give that a little bit of thought. So lots and lots of phone numbers for users of the app. I think the link to this is in the credits section, although this post is no longer available. It's no longer online. You can go hang out in these dark market forums. I don't necessarily encourage you to. You can. It's a good way to get on government watch lists if you do. So WhatsApp is a secure messaging app. So if there were a breach of a secure messaging app, it must have been an incredibly sophisticated hack by really super high caliber hackers. So let's take a look at that. And to get there, we're going to have to talk about click to chat. So click to chat is a feature of WhatsApp. And what it does is you create a URL. The URL begins, as they all do, with HTTPS, and then you point to wa.me, WA for WhatsApp, and then you follow that with your phone number. And that gives you a really easy link to click that will then initiate a chat connection like you see in the lower right-hand side of the slide. And that's great. So if you do that and you click on that link, you'll get a thing saying, do you want to chat with this person? Great. What if that person doesn't have a WhatsApp account? Well, then you get this. So it immediately tells you, without connecting to them and without doing any of that, it immediately tells you whether or not that number is associated with a WhatsApp account. So now I can check to see if you have an account on this service. And we've already talked about this before, but that's kind of a bad idea. You don't want to give attackers or potential attackers any more information than you absolutely have to. And so this immediately communicates something. If we had gone to the little continue to chat button, regardless, and you click that and it initiated a chat connection, and then it told you that person, you connected, or it said that person's not available to chat, then you wouldn't necessarily have known, right? Maybe they're not available to chat because they're not available. Maybe they're not able to chat because they don't have a WhatsApp account. So there you go. But instead, we've chosen to give out information. All right, fine. This lets me determine what is and is not a valid phone number for WhatsApp. And in one of these really cool hacker movies, someone would write a script and it would rip through all of the phone numbers for a country and check them all, and you'd build this database. But, it's easier to just Google, because Google's already done that. They've gone through and they have built up this record. So you can go straight Google for results. And in this case, I did a search for the site wa.me, and I looked for +44, particular country code, so I could go find numbers on that. I didn't want to spy on Americans from the United States, so instead I spied on a different country's users and then blacked out and redacted the numbers that came up. But a lot of numbers came up. You can see about 959 results are there. Now, that's not great. And since then, this has been reported, and people have been taking this a little more seriously. And you may still be asking, why does it matter? Why does it matter if someone knows that I have a phone number associated with WhatsApp. That's not my login. It's not my password. It's nothing like that. Why does that matter? Well, before we get to that, I will tell you that Google has been removing this information from the index, or at least they say they have. There are some, if you have strong Google foo and you can find some clever ways to search for that information, you may still be able to find some of it. That's all I'll say. And some people have left WhatsApp. And conveniently, if you'd like to know if someone has left it, you can go click on that and it will tell you link no longer valid, giving out more information about who is and who is not on WhatsApp. Not great. Don't do that. But why does it matter? Well, if I know that you're on WhatsApp, let's say I know someone. I know Sharon. And I know Sharon knows Jim, right? Jim is, let's say, Sharon's husband, or Jim's a good friend of hers. And I know they're on WhatsApp. I can now connect and say, hey, Sharon, this is Jim. I got a new phone, etc. And then I can use that to socially engineer my way into getting bank account information or money or whatever. And even if that's not the case, I can just reach out to them and say, hey, the following thing has happened. You have to be notified on WhatsApp. Here's your notification. Click this link. And then there you go. Before long, I've been able to get them to click a malicious link or do whatever. The thing I'm showing over on the right-hand side of the screen is not a malicious WhatsApp. It's just a message that I got, which is super legit, right? My package has arrived at the warehouse, but it couldn't be delivered because of incomplete address information. I want my package, right? So you can see they gave me a link to click, https uspsncs.top. That's the most legitimate United States Postal Service link I've ever seen. And it came from a truly legitimate site, right? It came from PLM IM WTF PXPB at Hotmail. Great. That sounds almost too legit to quit. And they also prompt me to reply with a yes and so forth to activate the link, whatever. Good heavens, right? This is simply there to try to steal stuff from me. Social engineering is the point. And, WhatsApp is a fine app, by which I mean they got fined for this. They were fined 265 million euros over this data protection breach, and they've been fined before, and I'm sure they'll be fined again. So there you go. And that takes us into our main topic, which is continuing our discussion of privacy. And if you recall last time, we talked about a few different things. K-means, we talked about distance, we talked about maybe maximizing entropy, all these other little tactics. But they all sort of broke down to K-anonymity. And that was not great because we saw there were a lot of ways to attack K-anonymity. And so let's back up a minute and let's try to think about what makes something private. And let's try to draw an analogy to cryptography, because cryptography seems to be doing fairly well. And they have a nice way of thinking about what security is. A crypto system is secure if, let's say, Alice sends a message to Bob, and Eve intercepts that message, but Eve can gain no information from that message. Right? Alice and Bob are able to communicate, but an observer cannot tell what's going on. They can't gain any information. Right? They have no more information after observing it than they did before observing it. And we can try to push that over a little bit toward privacy by saying, suppose Alice is sending a message to Bob about one of her 3 cats. And you have an a priori distribution. You think the message is probably about Mr. Bigglesworth. Maybe you have a 50%, you think it's 50% that it's about Mr. Bigglesworth. And it could be about Salem, and it could be about Jonesy. You have no other information, so you give them about 1/4 each. But you're sure it's about one of the cats, you're just not sure which one. So the message gets sent, you observe the ciphertext, and your distribution stays the same. You say, well, I think it was probably about Mr. Bigglesworth, but it could have been about Salem or Jones. I don't know. No information gain. We'd like that same kind of thing to be true for privacy. So suppose you perform some analysis on a data set. So let's posit this as a possible way of expressing privacy. Privacy is preserved, we'll say, if at the end of the analysis, you don't know any more about an individual in the data set than you knew before the analysis. Boy, that would be great, wouldn't it? So I give you this big data set. You can do any analysis you want to it, but when you're done, you're like, I don't know anything more about a person. I think they're in the data set. Maybe I know them in the data set, but I know no more about them than I did when I started. That'd be great. So as an example, continuing our cat analogy, we know the cat Jones, that beautiful cat off to the right there, is in the data set. And we know Jones's age is somewhere between 10 and 14, but after performing the analysis, we don't know any more about his age than we did before. Maybe he's somewhere in the range 10 to 14. That's all I know. That's all I can say. So that would have preserved Jones's privacy. And if you know who the three cats are, great. You're my kind of person. So this is a helpful analogy. It helps us think about what it means to be private, but it is just an analogy. Don't get too hung up on it. Right? In crypto systems, Alice and Bob communicate. Right? We want Alice to send information and Bob to get the full benefit of that information and Eve to get none. But in the world of privacy, we have a data curator and we want the analyst to be able to gain information. Right? We want the analyst to get information from that analysis. That's why they're doing it. We just want to protect the identity of people who may be in that data set. And so there's going to be information gain. It's inevitable, but we hope there's not enough to break the privacy of the individual. So we're close on this. Maybe we should revisit this and think about this as information gain, maybe information gain about a particular individual, but maybe there's something else that we can come up with. So if an analyst gains some information from the query, it's inevitable the analyst will gain information about specific people in the population. And as an example, let's think about this. Suppose we're studying the class you're taking right now. We discover there's a statistically significant link between taking this class and self-reporting depression. I feel bad, but hopefully you don't. Nevertheless, while an analyst can't determine whether you reported depression or not, right? They can't look at the data set and they can say, I know Tim is in this class, but I don't know if Tim has reported depression. However, I know there's a statistically significant link between Tim being in that class and people in that class reporting depression. So I don't want to hire Tim because Tim might raise my insurance rates. So there you go. Now, is Tim in the data set? Well, he might be, he might not be. Maybe he participated in the study, maybe he didn't. The point here is Tim's participation, or lack thereof, didn't adversely affect his outcome any more than if he had or had not participated, right? Whether he was in there or not didn't matter. The study resulted in this connection. That connection might adversely affect Tim, but not because he was in the study or because he wasn't in the study. Okay? Information was gained, and the real-world analogy of this is smoking, right? We study the effects of smoking. We find out that it leads to lung cancer and emphysema and heart disease and a bunch of other problems. So if you're a smoker, this is going to adversely affect insurance rates and so forth. And it's not because you participated in a study, it's just because we found out something about a class that happened to include you. So that'll be our standard for privacy, is that it shouldn't be the case the participating or not participating or being in a particular data set or not being in a particular data set has a negative impact on a specific individual beyond just whatever information is gained. So let's go back to our friend the spinner. So here's our friend the spinner, and not terribly sophisticated, but it had very strong privacy guarantees. Remember, it gave you this very strong deniability, and that was because it adds random noise to the results. Right? I didn't know if you landed in A or B. I didn't know that. I knew it was more likely, slightly, for you to land in A than B. But since I didn't know which one it was, I didn't know how to interpret your specific answer. And if I interpreted it, or if I told you I was interpreting it in a particular way, you could just tell me I'm wrong. And I could be wrong, right? Because each spin was an independent, identically distributed trial. That wasn't true for k-anonymity. K-anonymity was constantly being attacked, and there were challenges to it. And why was that? Well, k-anonymity was very deterministic, right? We had an algorithm we applied to the data set to merge some things, to generalize some categories, or to drop other categories. And that deterministic nature could lead to a particular outcome that when we looked at it later, we could say, you got to this result by doing the following things. And that might let us reverse engineer what was going on. That was the downcoding attack. It turns out in the paper from 2014, they actually anticipated this. And they said, let's think about privacy-preserving algorithms and consider deterministic and non-deterministic algorithms. Non-deterministic algorithms being algorithms that rely on random information. These algorithms are applied to queries to preserve the privacy of the subjects in the dataset. And here's their argument against deterministic algorithms. So let's be sure that you follow this. A deterministic algorithm is non-trivial if and only if there's a query, and I apply that query to two different databases, and that query yields different outputs for each of the databases. Okay? So I ask to say, how many rows are in this database? And I apply it to D, and it says 17. And I apply it to D prime, and it says 19. Okay, that gives me a different number. So that query is in non-trivial. A trivial query would be, always return the number 17. So I give it D, I get 17. I give it D prime, I give it anything, I get 17. Or I say, is this a database? And it says yes. Well, any database is going to give me a yes. So that would be trivial. So a non-trivial allows us to distinguish between two databases, at least two databases. Now, let's start with a particular database, D, and let's change a single row. That gives us a new database. They differ by a single row, but it gives us a new one. We'll call that D prime. And we'll check our query on those two, and it might give us the same result. If it does, okay, that's fine. I then make D prime, my new D, and I change a row in the new D, and that gives me a new D prime, and I compare them again using F. And I keep changing rows until I encounter a situation where F gives me a different result. And we know it will because it's non-trivial. The last two versions of the database on that path give different results for F, right? I stop as soon as I get a different result. And they differ by a single row because I changed one row at a time. So that means F is a query that allows me to distinguish between D and D prime based on a single row. Okay? An adversary, knowing the database is one of those two, learns the value, or at least constrains the value, of the unknown row. So they've learned something about a single row or a single entry, a single individual in that database. And they conclude there's no privacy-preserving deterministic algorithm because of this. And unsurprisingly, this is essentially the downcoding attack that was reported in 2022, in this case reported well before in 2014. So what this says is deterministic privacy-preserving algorithms, it's not the way to go, right? What you want is something a little different. So let's go back to our friend the spinner, and let's try to do a little bit of randomization. In this case, I'll use coin flips because that's the example given in the paper. But we'll turn back to I like the spinner a little better for a lot of reasons. It's more visual than this sort of thing is. So let's perform a query that results in a yes or no result, right? We'll say, has Tim been diagnosed with HIV? And maybe I don't say that directly. Maybe I'm like, has a male aged 25 to 30 living in Hartford, Connecticut at this zip code and with these characteristics been diagnosed, and I've determined that so I can select Tim from the population. The system flips a coin. If it's heads, it returns the truth. Okay, that happens about half the time. If it's tails, it flips a second coin, and if it's heads, it always says yes. And if it's tails, it always says no. So now I don't know, right? I mean, maybe I get a yes, and I'm like, well, I guess, but I'm not sure. So the true fraction of yes is, if we think about, the spinner here, and we think about the true fraction of yes being p. In this case, it would be whatever it is, whatever the population value is when we land in that section that says tell the truth, right? We flip the coin, it's heads, we tell the truth, the true fraction of that is p. So for a total of q queries, we expect to have pq yeses come from that section. But we also expect about a fourth of the queries, so q over 4, to land in the place where we always say yes. And so the total yeses we'll get would be pq plus q over 4. Now, we can use that to estimate p, and we've done that in class before, right? We take the number of yeses, we subtract q over 4, right, the artificial yeses, we divide by q to normalize it, and we wind up with the fraction, right, the percent of true yeses or true yes results in the population. And you can see that larger q will yield lower variance, right? Variance is going to be roughly proportional to the square of q. So we can expect it to be more accurate because of large number laws. So as it gets larger and larger, q gets larger and larger, we expect our estimation of the population fraction p to get better and better. So let's talk about neighbors and sensitivity. We've actually already seen the idea of neighbors. I have two data sets. They differ by a single row, right? Maybe D has a row, D prime doesn't. Maybe D prime has a row, D doesn't. Or maybe, like you see in the picture, they differ in that D includes one individual, D prime includes a different one there, okay? So they differ by a single row. And we will typically, for a lot of what we're going to do going forward, we'll think about removing a row from D to obtain D prime. But there are other things we can do. We could add a row. We could change a row. But the point is they're neighbors because they differ by a single row. Sensitivity is a key idea that we're going to need going forward. So let's say D and D prime are neighboring data sets, right? They differ by a single row. F is our query. Right, it maps our data set onto some result set. Often when you're looking at the math of differential privacy, people like to use R to the N, right? They like to use this beautiful connected subspace. But really, all we need is for F to map from the data set onto some metric space. And as long as we're going into a metric space, I can then talk about the difference between the results of the query, how far apart they are. And I can write that, as I do down at the bottom of the left-hand side, as the maximum distance between the results of the query. So the maximum over the neighbors, the maximum amount that this can deviate. and I'll call that delta F. And delta F is the sensitivity for that query, right? It's specific to that query. So, how do we do that in practice? Well, over on the right-hand side, we have a table. And we have some names and some ages. Okay, if we have a query like, what is the length of that table? In this case, that will return 8. A neighbor, right, a neighbor of this would differ by a single row. So perhaps I remove a row, in which case the answer would become 7, and the distance between the original and its neighbor would be 1. Or maybe I add a row, in which case, again, the distance between the original and its neighbor is 1. Or maybe I change a row, right? Maybe I go in and I modify Linda Sarsour's age, and now the distance, the query returns exactly the same result. It still returns 8 for both, and the distance is 0. So the maximum distance I can have for a counting measure is 1. So the sensitivity for a counting query is 1. It'll always be 1. That's great. This was easy. That was easy, right? Sensitivity seems like it's an easy thing. Let's go on and think about the mean. Okay, what's the most I can change the mean of this data set? Well, I could drop a row. That's something I can figure out, right? So let's think about removing an element. So if we look at that data set, which element do you think removing would change the mean by the most? Well, the average of the age column is 44.25. And Samira Ibrahim is the farthest from that. Her age of 37 is the farthest from the mean. So if I drop her row, I'll change the mean by the greatest amount. And so I do that, and the new mean is 45.29 for a difference of 1.04. This means that the sensitivity for this data set for the query of the mean for this data set is 1.04. So clearly the sensitivity depends on the query, and it may depend on the data set. That's important information. Sensitivity depends on the query and the data set. So once we know the query, we can then try to determine how to compute the sensitivity for a particular data set. Now, you may be asking, what if I added a row? Or what if I changed, let's say, Linda Sarsour's age to 80? Wouldn't that be different? Yeah, it would be. We'll come back to that. But for now, we have all the tools we need to begin to talk about differential privacy. So let's get into that. Let M be a function that maps a data set to a value. What is that called? It's a query. It's a query, right? Select star from people where age equal 25. There's my query, right? So M is just a query. Then we say that this is differentially private or a mechanism. Mechanism is the key word here. That's why we're calling it M. It's a differentially private mechanism if and only if for all neighboring data sets, right, data sets that differ by a single row, and for all possible outputs S, right, everything I can get back from that query, the following equation holds. And there's a lot to unpack here, but trust me, we'll walk through it. It's not that hard. So over on the left-hand side, we have a probability. And over on the right-hand side, we have a probability. What's in these probabilities? So on the left-hand side, we have the probability that when I apply the query to a dataset D, I get back some output S. And over on the right-hand side, I apply the same query, M, to a neighboring dataset, D prime, and I get back the same result, S. And the reason we're using set notation here is because I might get back, I'll have a set, I can have a set that is a small interval around a value, And as long as I'm in that small interval, I'm basically the same. So over on the right, I apply the query and I get back 1.023. And I apply it on the right and I get back 1.0235. It's effectively the same, okay? Sometimes you'll see equals there, but in the paper they use this notation like this. So basically what happens is I get the same result to my query on both D and D prime. And I ask about the probability of each of those queries returning that result. Now you may say a query is going to return a result, right? A query is a function. Functions give you the same output for an input. So what do you mean? Well, a deterministic function does, but a non-deterministic function might give you different results. And so in this case, what I'm seeing is that I have a couple different possibilities, and the probability of getting the same result from the data set and its neighbor is conditioned by that constant right there in the middle, that E, which is Euler's number, to the power of epsilon. So you can see if I divide both sides by that probability on the right, I have the ratio of the two, and I'm saying that ratio has to be less than or equal to E to the power of epsilon. So if epsilon is 0, then they have to be equivalent, right? Because the ratio would have to be 1, right? E to the 0 is 1, so that ratio has to be 1. So, for example, if epsilon is 1, then I get e to the first, which is, 2.718281845904523, I think. So that would let the ratio go up to that number. It's like it differ by quite a bit. In fact, the higher epsilon is, the more I allow those probabilities to differ, okay? And the less likely it is that they give the same result. Or I should say, the greater is the likelihood that they give different results. Because again, these are probabilities. So this requires some more thought, but I think hopefully you get the idea on this. And this gives us if this is true, if this statement is true, then M is a differentially private mechanism. So the parameter epsilon, we can think of it as this knob that we can turn to control the degree of privacy. As we turn it closer and closer to 0, then the two become indistinguishable, right? The probabilities converge to the same, and I can't tell which data set is which. And I sort of provide maximum privacy. And as we turn it up to higher and higher numbers, the probabilities are allowed to diverge, and it's more likely I'll get different numbers between them. Suppose I turn it really high. Suppose I turn it to like 100. Then the probability that I get a result from D and the probability I get a result from D prime, right? It's almost guaranteed that they'll be very different. And now I can tell the two apart and learn something about the data set. So in general, we want epsilon to be closer to 0. And generally, we want it to be less than 1. As a good general rule of thumb, you would like epsilon to be less than 1. If epsilon is greater than 10, well, we can't really guarantee any privacy. Now, this is kind of abstract right now. We'll try to make this a little more intuitive as we go along. Okay? We call epsilon the privacy budget, and we'll see why we call it that a little bit later on as well. So let's go back to our friend the spinner. Remember the spinner? So here is the spinner, and now we're going to be looking at it through the lens of differential privacy. So suppose we choose a question. In this case, our question is going to be, are you a member of the Communist Party? So we know you're a dirty commie, and we're going to try to find out. Or at least we think you might be. So we're going to ask you that question. So we go and we ask people that question, are you a member of the Communist Party? And if you say yes, you spin the spinner, and then you say yes, what does that tell us? Well, a couple of things could have happened, right? The spinner could have landed on truth, and you told us the truth. Okay? Or the spinner could have landed on yes, and you were obligated to tell us yes. The one thing we know didn't happen is that the spinner didn't land on no. Okay? So we can start to express the probability of seeing a yes. And we have two possibilities here, right? We get a yes when yes is true, and we get a yes, but yes is false. So assume yes is true, right? That's what this little conditional probabilities tell us. Assume yes is true for the left-hand side. If yes is true and I spin that little spinner, I'm going to say yes when it lands in truth, and I'm going to say yes when it lands in yes, and I'm going to say no when it lands in no. So the probability then of me saying yes, given that yes is true, is 75%, because 75%, that half of it is truth, a quarter of it is yes, the total of that is 75%. The probability that I say yes when yes is false, right, that only happens, if yes is false, that only happens when I land on yes, which is 25% of the spinner, and so that probability is 25%. So I wind up with 0.75 less than or equal to e to the epsilon times 0.25. I divide both sides by 0.25, and I get 3 less than or equal to e to the epsilon. And I can solve for that, right? I can take the natural log of both sides, and I get epsilon equal to 1.098. So now I can say this spinner is 1.098 differentially secure. I've given the privacy afforded by this spinner a number. It's a little greater than 1. What about the spinner from the homework? Remember it? We had those 3 sections. Each one was about 1/3 of the total circle. So in this case, what's the probability of answering yes, given that yes is true? Well, 1/3 of the time we're in truth, so we answer yes. 1/3 of the time we're in yes, so we answer yes. So that's 2/3. What's the probability of answering yes, given that yes is false? Well, that only happens when we land on yes. So we have the probability of answering yes, given that yes is true, as 2/3. And the probability of answering yes, given that yes is false, of 1/3. Right? 2/3 plus 1/3 is 1. Right? That covers everything. And so when we plug those in, we wind up with 2 less than or equal to e to the epsilon. Right? 2/3 divided by 1/3 is 2. When we solve that by taking the natural log of both sides, we find out this spinner is 0.693 differentially secure. The epsilon is a smaller value. Not quite, but getting close to half. And that tells us that this mechanism is more differentially secure than the previous one. And that makes some intuitive sense, right? In this one, truth occupied about half of the spinner. In this one, it only occupies about 1/3. So we have a mathematically rigorous way to talk about the privacy afforded by a given mechanism like this spinner. And we can actually rank things. We can say this is more private than this. That's pretty powerful. We didn't have that before. Now we do. I think that's pretty neat. The general way we implement differential privacy is just what you saw. We add some random noise. We can't add too much noise, or the result won't be usable by an analyst anymore. But we can add a fair amount of noise. And that depends on a couple of things. It depends on the data set, and it depends on the query. Right? We've already decided that remember sensitivity? We'll come back to it in a bit. But sensitivity tells us something about the amount of noise we have to add. So for instance, suppose you ask a data set of the census for the number of people who identify as Hispanic in Tennessee who are above age 40. That's going to be a fairly large number. And you're not going to reveal much about who those people are and where they are in the state, etc. And so we probably don't have to add any noise to the result of that. However, if we are more specific, let's say we go to a particular county. Coffee County is where I grew up. And we look for people who identify as Hispanic below age 10. We have a fairly small population. And releasing that information could be problematic. And so we need to add more noise to make it more secure, more private. So the idea is that some queries are more sensitive to changes in the input than other queries. Some are more sensitive. Some will just require more noise to protect them. So let's think for a minute about information gain. So suppose we have a hypothetical person. Let's call her Sunya. And let's say Sunya answers yes based on the 1/3, 1/3, 1/3 spinner, the one from homework. Okay? So he turns around, spins the spinner, turns back around and says yes to our question about whether she is a communist. Before she spun the spinner and answered, we had no information about whether she might be a member of the Communist Party. But now we have possibly some evidence, right? We have an answer from her. And let's see if there's information gained from that. So we have a couple of things. We have a hypothesis, which is that Sunya is a communist, and we'll just abbreviate that as communist. And we have evidence, and the evidence is us observing her response of yes. So let's write down some things we know. We know, let's say, that our prior belief, right, is that maybe she's a communist, maybe she's not. We don't have any information, so our prior belief is at best 50-50, right? It's 50% likely she's a communist, 50% likely she's not. We don't know, okay? We then have some information. The probability that we observe a yes, given that she is a communist, is 2/3, right? We got that earlier, right? The probability of observing a yes, in this case, given that she's a communist, that would happen because she landed in truth or because she landed in yes, and so that's 2/3. Okay, we'll call that the likelihood that Sunya is a communist given the evidence. So we have the prior, we have the likelihood, but now, at the end of the day, we want to have probabilities. In order to convert these things into probabilities, you typically normalize them, right? You divide them by the total probability. In this case, we want to know what's the total probability of observing a yes. Now, here's where our priors have to come into play again. I don't know the actual probability of observing a yes. That in order to actually know that answer, I would have to know whether Sunya is a communist or not. But I don't know that. But I have a prior belief. My prior belief is 50% yes, 50% no. And so that's what I use. I use my prior information. So the probability of yes, given that she's a communist, is still 2/3. The probability that she's a communist is 1/2. So I multiply those two together and get 2/6. The probability that she says yes, given she's not a communist, is just 1/3. And the probability she's not a communist, again, 1/2, because I don't know. And so that would give me 1/6. So I add 2/6 plus 1/6 is now 1/2. And so that's my marginal likelihood that I will use to normalize. What do I do with these numbers? I plug them into Bayes' rule. So if you're not familiar with Bayes' rule is an important tool that we use to estimate a number of things. We can use it to estimate the information gained by an observation or to update priors. Most commonly, we use it to update our priors. And you see it over on the right-hand side. And the important pieces are our prior belief, right? That's the probability that A is true. Right? That's our prior belief. We think this about A being true. We have a likelihood, right? We have some evidence. We observe B. And so we say, what's the probability of observing B given that A is true? And then we divide the whole thing to normalize it by our marginal likelihood. What do we think the total probability of observing the evidence B, what do we think that is? And that gives us our posterior or updated probability. This is how we update the belief, right? And so this is the probability of A given the observed evidence B. So let's plug in, this is pretty abstract. Let's plug in the stuff that we've already looked at from a couple slides ago. And so our hypothesis is that Sunya is a communist. So we'll call that probability communist. And then we have the probability of observing the yes given that she's a communist. We divide that by the total probability of observing a yes, and that gives us the probability that she's a communist given that we observed the answer yes. And we plug everything in, we get 2/3. So our initial probability distribution was 50% she is, 50% she's not. Our new updated probability distribution with this one observation is 2/3 or 67% she is, and 1/3 or 33% she's not. So I've changed the distribution based on observing a piece of evidence. And it might feel like I have a lot of information. I went from 50-50 to 67-33. That may seem like a big shift. But in reality, I've only gained about 8/100ths of a bit of information. How do I know that? Well, I can take the Shannon entropy of the two distributions and just take their difference. Okay? I'm not going to go through all of that, but entropy is, it's basically the probability times the log of the probability. You sum those up. In this case, we do it with log base 2, so we can talk about bits. We wind up with about 8/100ths of a bit. So very little information was gained by this question, which is good, but it's not zero, right? The probability distribution changed. I could conduct more experiments, and maybe that would further change my probability, right? I might ask Tim if he thinks that Sunya is a communist, and maybe that would change things. But I've gained very little overall information, and that's great, right? That says something about the privacy afforded by the spinor mechanism. It's not perfect, right? I didn't fail to gain any information, but it's pretty good. I didn't gain enough information to really be conclusive, right? I can't really blackball her and keep her out of movies in the 1950s because she's a communist. So let's further visualize this, and I like this visualization. So here we have, across the bottom, our initial suspicion. What do we initially think? And on the vertical axis, on the y-axis, we have our updated suspicion. What do we think after performing our query? And the colored bands represent different values of epsilon. So if we look over at the scale, so over here just to the right of the image, we can see that down here at the bottom, close to 0, we're in the purple area. Right below 1 is purple and dark blue. And that puts us really close to this 45-degree line. Now, the 45-degree line is the no information gain line, right? If I start out, let's say at 50%, and I go up, and I meet this line, and then I go over, I'm still at 50%. But you see, these bands allow me to move away from that a bit, and that's because the mechanism is probabilistic. Okay? It's probabilistic. And so I can land anywhere in this region here with that particular epsilon. And so I can gain a little bit of information. But I'm going to stay close to this 45-degree line, and so I'm not going to gain very much information. Now, suppose I let epsilon go way on up here. Say I let it get up above 7, or close to 7, and in this red and orange area right here. And suppose I start out with my 50% belief, and I go straight up until I encounter red and orange, and wow, it's up here almost at 100%. So I start out with that. I have an epsilon that's a pretty high number. I'm almost certain that this person is a communist, after I have that one observation. And you can see that, going down here, let's say 3 down here, 3 is right about here. I go up from that, and I wind up here, and now I'm like 80% sure the person is a communist, okay? So this sort of shows you how the epsilon values can work to modify your priors. And this was all built using using Bayes' rule, the same thing we just looked at. So the closer epsilon is to 0, the less information gain an adversary is capable of. But you can see that drops off pretty fast as epsilon goes to higher and higher whole numbers, like 7 up here, or higher than 7. Okay. Now, this lets us do some reverse engineering of the spinner, which lets us further visualize what epsilon means. So suppose I want a spinner that gives a specific privacy guarantee. I want a particular value for epsilon. Well, I use my little equation for differential privacy. You see it right there, right? The probability of yes, given that yes is true, is less than or equal to e to the epsilon times the probability of yes, given that yes is false. I divide both sides by the probability on the right, and I wind up with the ratio less than or equal to e to the epsilon. So epsilon tells me, in this case, the ratio that I need. Suppose that I want a privacy budget of 0.1. That's a pretty good one. Then I need a ratio of approximately 1.1, right? Because e to the 0.1 is 1.1. So that tells me the ratio of the two needs to be 1.1. So if I devote half of the spinner to yes, then that's 180 degrees. Then I need 0.1 times a half, which gives me 18 degrees for truth. Does that make sense, right? The total that I would get for yes needs to be 1.1, okay? And so 1 is the yes, and the 0.1 is the truth, right? That 0.1 is 1.1 minus 1, not the original epsilon. So a tenth of 180 is 18 degrees, so I have 18 degrees for truth. The remainder is no, and we wind up with the spinner like we see over on the left. And you could reasonably believe that spinner would give you pretty good privacy. In fact, it's going to give you epsilon differentially private mechanism where epsilon is 0.1. We could try this with the other spinner. Remember the first spinner we ever looked at, the one where we had to do all the fancy math to get the maximum likelihood estimator. Okay? We have these two regions. In region A, you tell the truth. In region B, you lie. So I spin the spinner, and I say, are you a member of the Communist Party? And I answer yes. What happened? Did I land in A and tell the truth, or did I land in B and lie? Again, I want to be epsilon differentially private. And so we can work this out, right? We know the probability of saying yes, given that yes is true, is P, right? It's the portion of the spinner for A. And the probability of saying yes, given that yes is false, is 1 minus P. It's the remainder of it that's in B. And I know the ratio of the two, right? P divided by 1 minus P is the same as it was before. And it turns out, when we solve all of this, I need P to be 0.525. That means that 52.5% of the circle needs to be truth, and the remainder can be lie. So that turns out to be 189 degrees for truth and 171 degrees for lie, which is the situation we see there on the right. And if you look, you can see that sure enough, the one angles up just a little bit. So again, I spin the spinner, and now I have the same epsilon differentially private guarantee as before, 0.1. And you can sort of see this is going to give me pretty good privacy. So far, we've been dealing with a binary choice, right? Yes or no. I'm a communist or I'm not a communist. But what about continuous data? Suppose we want to know what's your age, or we want to know the average of something, or we want to know the total number of people that fall into a given category. that kind of data, well, this approach isn't going to work for that. Right? We need a mechanism that handles continuous data. And that's going to turn out to be the Laplace mechanism. Now, there are many different mechanisms that we can use. There's some based on the Gaussian stuff. There's a Gaussian mechanism. There's a bunch of them. But the Laplace mechanism is sort of the king of most of these differentially private mechanisms when it comes to this kind of data. The Laplace mechanism depends on the Laplace distribution. And the Laplace distribution is just a probability distribution that happens to have some parameters that control it. We would call that parametric distribution. Might call it a family of distributions, right? Where each member is a different choice for the parameters. And there are two. The first parameter is the mean, right? Where do we want the distribution to be centered? And if you look at the top right, you'll see the effect of changing the mean, right? 3 of the curves are centered on 0. They're centered with the mean at 0. And that 4th curve, it's light green if you can see that, is centered at -5. So it's shifted to the left by 5. And that's just because we chose that for the parameter. The second parameter is the scale parameter. And in that little diagram, it's b, which is the scale. And if we could get to a b of 0, we would have everything piled up right there at whatever the mean is. So we have a perfect straight-up spike. Obviously, we can't have that, so that's not possible. And so we have a b that's greater than 0. And we can see an effect of a few of those, right? b of 1 is that tallest one. 2 is a little bit shorter. 3 is a little shorter than that, etc. So as we increase the scale factor, we flatten out the curve. And we can see what that does to probabilities if we look at the cumulative distribution function, right? The total under the curve as we move across. That's what we see below on the right. And so sure enough, you can see for the one that's been offset, it rises fast, has a sort of S shape to it because there's still a little bit past the peak that we accumulate. With the red one, we have it low until we get very close to the peak, and so most of the probability is concentrated around the peak, etc. So as we flatten it, as we increase the scale factor and flatten the curve out, we increase the probabilities of values that are far from the mean. So we basically fuzz up the noise more as we increase the scale factor. You can think of the scale factor as turning up the noise level. We increase the probability of generating results that are farther from the mean. Okay, now, given all of this, the way we use this is that we add Laplace noise, right? We add randomly sampled, we create a Laplace a Laplace distributed random variable with the given parameters, and we sample from that to get the Laplace noise. We add that to whatever the value we would get from the query is, and that adds some random data to it. And we add Laplace noise with center 0 and scale S over epsilon. Okay, so we know epsilon is the privacy budget. So as epsilon gets smaller and smaller and smaller and smaller, it's on the bottom of that fraction, right? As the number on the bottom of the fraction gets smaller, the scale factor gets larger. And so as we let epsilon get small, we increase the scale factor, we flatten the curve out more, and we increase the amount of noise. S goes on top. S is our sensitivity. Remember the sensitivity? The sensitivity is the amount by which the two data sets will differ, right? The amount that a change will cause the two to differ, or cause the probability of selecting from one of the two to differ. Basically, it tells me how easy is it to tell them apart, right? And at 0, I can't tell them apart, which is the perfectly private example. So smaller values of S in that fraction will, of course, lead to larger lead to smaller values, smaller values of S lead to smaller values, because it's on top of the fraction, of the scale factor, which means that I have more and more of a spike. Hope all that makes some sense. And so we combine the two into S over epsilon, and that's going to be used as the scale factor for our Laplace distribution. Whew. Why are we doing that? Turns out the math works out. It just works out beautifully. So the Laplace mechanism, we take the original query, f of d, we add some Laplace noise centered at 0 with scale factor sensitivity divided by the privacy budget, and that is our new, we claim, epsilon differentially secure mechanism. Is it really? I mean, I've just been giving you a bunch of assertions. Well, in the paper, in the paper that's cited and in iLearn, there is a proof of this, and I pulled what I think is the most salient part of the proof out. We can go through it really quickly here, but basically you can see what's happening. Up at the top, we have the ratio of the two probabilities, and we then break them down, and we say, well, that's going to be e to the power of, and you can see here's our little epsilon in here, and here's our difference divided by the sensitivity. Here's our epsilon again, and our difference divided by the sensitivity. Where did this come from? It came from the Laplace mechanism, okay? So now we know what the ratio of those two probabilities should look like. We're dividing here, dividing this guy by this guy. And so they're both, e to the power of something. So we can convert that division of two exponentials, to exponentials. There we go, right in a minute. I'm tired, sorry. The division of two exponentials can be the exponential of the difference of the powers. So we write it like that. Here we have minus zi and minus zi over here. So that goes away, right? It's minus zi minus zi is minus zi plus zi, 0. And I wind up with just that difference right here. But that difference over all the possibilities is just the distance between the result of those two queries. And that is this little norm right here. And we agreed early on, way back several slides, that this was the sensitivity which we represented as delta f. And so we have delta f divided by delta f. That becomes 1. And we have the little epsilon here. That comes down here. And then we wind up with the ratio of the two probabilities is e to the epsilon. It just works out. And so that's our Laplace mechanism. So the noise that we add with the Laplace mechanism depends only on two things. The sensitivity, which depends on the query and could depend on the data set itself. Remember, sensitivity depends on two things, the query and the data set. And our arbitrary privacy budget, epsilon. Pick whatever privacy budget you want. Right? We've already sort of seen the effect of that. So it depends on those two things. So how do we generate Laplace noise? So if you look over on the right-hand side, I've used Python to do it. I imported NumPy, the Python package you can grab and install. And NumPy will let me generate a Laplace distributed random variable with a given mean and scale factor. And so in this case, that's what I've done. I've told it, put the mean at 0, set the scale factor to 10, and give me a Laplace distributed random value. And in this case, I get 26.28. Okay? I could write a function to do that. And in fact, I did, right? There's a function right there for Python. Define Laplace noise to take a sensitivity and an epsilon. And what do? I just center it at 0, and I use the scale factor of sensitivity divided by epsilon and return it. So now I can say Laplace noise 1 and 0.1, and I get back a number. And we just add it to the result, right? So suppose we have a data set that contains people who've tested positive for HIV, and we count the total number of people in that data set, and it turns out to be 40,150. I want to add Laplace noise. The Laplace noise that I add depends only on the sensitivity of my query, right? And the epsilon value I've chosen. So suppose, right, I'm counting. The sensitivity for all counting queries is 1. The epsilon I chose is 0.1. 1 divided by 0.1 is 10. And so I put in 10 for my scale factor. Notice the scale factor doesn't depend on the size of the count. It doesn't depend, in this case, on the size of the database. So I plug that in, and I get a number. I get 26.28. I add that to the 40,150, and then I report, the thing I actually report as a result of the query is 40,176. It's not the true answer, but it's very close to the true answer. How close? Right? I worked it out on the screen there. It works out to be within 0.07% of the real value. That statement at the bottom is wrong. 0.07% of a percent? No. It works out to be 0.07 of a percent, or 0.07% of the real value. Sorry about that. So does it work? Well, suppose we carefully structure a query, because I want to know if Dave has been diagnosed with HIV. And so I construct a query to select Dave. I say, okay, I'm looking for a male, age 25 to 30, who resides in Hartford, Connecticut, has brown hair, blue eyes, over 6 feet tall. All right, so I start giving all these characteristics until finally I'm pretty confident I'm going to select Dave. And I plug that in, and let's say the answer is 1. So what I'm going to see is I'm going to see one of those values over there, right? It's going to report 6. It's going to report 6. And I'd be like, 6? Okay. Or it's going to report -5, or 0, or -5, or 9, right? And it's not going to tell me 1 or 0. Now, if I'm able to ask the question repeatedly, a whole bunch of times, and we'll talk about this later, a whole bunch of times, then sure enough, large number laws will let me decide with arbitrary precision whether the answer is 1 or 0. I can tell you what the mean is. As long as I can just keep asking as many times as I want, I can get really close to the mean because of large number laws. Okay, so we have to prevent that from happening. But without that, I'm stuck, right? The answer doesn't tell me whether Dave's in the data set or not. Notice how much it deviated, right? I went from 1 to 9. Okay, in the previous one, I was really close to the true answer. But here, it's pretty far from it. So it provides excellent privacy for individuals in the set. Let's go back to sensitivity for a minute, because sensitivity is really key to making all this work. We're calling it sensitivity, right? The maximum amount a result can change when a single row is changed. We remember it being 1 for a counting query. That's great. We know what it is for counting. What is it for a sum? So suppose I know the maximum and minimum values for an item in a data set. Okay, I'm going to sum them up. How much can I change the maximum by adding or removing a row? Well, it turns out we don't know. We don't know because suppose I added a row with, I have a data set that has numbers that are between 1 and 100. But I add a row that has an entry of 1 billion. I'm going to skew the sum by quite a lot. Or suppose that I add a row with or I change a row. Say I change an existing row to be minus 1 billion. I'm going to skew the average a lot. But in general, that's not going to be what we do, and we need a better approach than saying, I don't know what the sensitivity is. And so for summing queries, we usually say the sensitivity is given by M, big M, minus little m, the maximum minus the minimum, right? We're assuming that values lie within some range. And that presumes we know the maximum and minimum value for an attribute. We could use the values in the set itself. That's what we did right above. That's possible. But it might not be the best approach. So earlier I gave you a table that had some women and their ages in the table. And we might ask, is there a natural maximum and minimum for that value? Okay. Well, no one, the oldest person, the time I'm recording this that I could find, was 122. So 125 is a nice, I won't say round number, but a nice number that is probably greater than anyone's going to live to. 125. So that'll be our maximum. We're not going to have any kids in our database because then we have different rules and we can get in more trouble. So no kids in the database. So we have a minimum value of 18. So now we have a maximum of 125 and a minimum of 18. And if we're just summing, we can say, well, the sensitivity is 125 minus 18. Great. I think that's what, 103. I can't do math today. I'm too tired. 125 minus 10 is 115. Minus 5 minus 3. So it's 107. So my random guess of 108 was wrong. So 107. So there we go. And we have a value for the sensitivity, but it depends on us making an informed but somewhat arbitrary choice for this parameter. Now, some parameters are not arbitrary. Suppose all my values are 0 to 1. Well, then I know the maximum and minimum. Or suppose I know it's minus 1 to positive 1. All right, I have a range for a parameter. Then sure, I know what those values are. But sometimes I have something like age, where I just need to say, I'm going to just invent a sensitivity for that makes sense given the data. So here's our table again. Here's our table of these women and their ages. And remember, the average of the age column was 44.25. And Samira Ibrahim's age was the farthest from the mean at 37. If we remove her record, it changes the mean by 1.04. So initially we argued that the sensitivity of the query for the mean of this table was 1.04. But suppose we add Manaz Afkhami to the table. She's still alive, and she's 83 years old, at least at the time of me recording these slides. That has a more significant impact on the average. It pushes the average up by 4.31. So if she's someone that can be added, the maximum age has gone up, and that shifts it by more. So we need a more general, maybe more conservative sensitivity for the mean. And here's what most people typically use. Remember, we used m minus n for the sum. We used 1 for the count. And so we can combine that and wind up with m minus, big M minus little m over n as our approximation for the sensitivity of the mean or the average. And so if you plug in values we decided on earlier for age, right? The maximum 125, the minimum of 18, total size of our data set was 8. We wind up with a sensitivity of 13.375. That's way higher than the sensitivity we initially got. On the other hand, if we use the maximum and minimum values in the table itself, we get 1.375. So we're getting sensitivity values all over the map here. And the point I'm trying to make is that sensitivity is at least a little arbitrary. You need to do a little bit of study of your data to decide where you want the sensitivity to be. What's the impact of it, right? The greater the value of the sensitivity, the higher the parameter to the Laplace mechanism, the larger that scale factor is, and the more flattened out the curve becomes, and the more noise you add. So for the 13.375, we would add a lot more noise. And that makes sense, right? The range is 125 to 18. If we just use what's in the table, it's much smaller, right? Because the ages that are in the table are I think there's one in the 30s and the rest are 40s. That's going to be smaller. 1.375, we're going to add less noise because of that. Standard deviation. Right, same problem, except more so. The mean is convenient because we can just look at the values themselves. Standard deviation requires us to think about how the values distribute around the mean. So now we have this sort of second order problem, which makes sense because it's a second order statistic. And we tend to use what you see over on the right there. The maximum minus the minimum divided by the square root of n. And so for what's in the table, we could plug in 48, that's our maximum age in the table, 37, that's our minimum, 8's the number. When we do it that way, we wind up with 3.889. It's a higher sensitivity because we're taking the square root of n, right? And so that results in a smaller number on the bottom and a larger overall value. Okay? If we look at the data set we have and we ask how much can we change it by just deleting a row, well, that's once again deleting Samira Ibrahim because her age is the farthest from the mean, and that results in a change of 1.4. If we use the limits for our age, right, that would be 125 minus 18 divided by the square root of 8, we get 37.8. So again, you see a wide range of possible sensitivity values. Determining the correct sensitivity is very important. Very high sensitivity values result in a lot more noise and may make your data less useful. Very, very small ones can make your data much more useful, but they might let you expose more information. So, for example, think about the ages we had here. They're all sort of clustered together. The smaller and smaller I make the sensitivity, the more differences in the ages matter. Okay, the more they sort of spread out because the region around the mean, right, the Laplace curve is flattened more, and so probabilities that are further from the mean are higher, and I wind up with more noise that hides these ages. But as I make it more and more of a spike, then I start to expose some of those outliers, especially Ibrahim's, which is down at 37. I start to expose those more. Let's talk about some properties of differential privacy. So differential privacy has some really wonderful properties associated with it. And the first one is sequential composition. And this is just almost magic. Suppose I have a mechanism M1, and it satisfies the epsilon 1 differential privacy. And I have a mechanism M2 that satisfies epsilon 2 differential privacy. And those can be the same value or different values. And I define a new mechanism that just does both. So I ask you, what is the mean and the standard deviation of this? And if you're willing to give me back both, the mean and the standard deviation, right? They might be two queries, but when I get them back, what happens is the result has differential privacy equal to the sum of the epsilons. So think about this for a minute, because this is getting at the answer to a question I posed earlier. Right? I keep asking you the same question. I ask you, what's the age? Or what's the, I ask you, I do that query to look for a particular person. And I get back 6, and then I get back 0, and then I get back 9, and then I get back 4. And if I'm able to do it enough times, I eventually narrow it down, right? Every time I do that query, I basically add that epsilon to it. So I start out with epsilon of 0.1. If I'm able to do it 10 times, they add up, okay? And now I've got an epsilon of 1. I do it 100 times, I have an epsilon of 10. And I probably am getting close to exposing the result. So they add. And that means if I'm going to generate both, I can only do that with a potentially higher privacy budget, a potentially larger value for epsilon. And larger values for epsilon have the potential to expose more information. Smaller values of epsilon have stronger privacy guarantees, so adding up this way could weaken it. But that also means, another way to think about it is, this tells me what I can let you do, right? If you want the mean, okay, I've got a privacy budget for that, I can let you have that. Oh, you want the mean and the standard deviation? I have to compute the new privacy budget for that, right? So suppose I want that to be 0.1. Then the privacy budget for the mean has to be something less than 0.1, and the privacy for the standard deviation has to be something less than 0.1, assuming I don't really want to be 0. And when I add them together, they're 0.1, then I'm okay. Sequential composition is a little better. So I want to release multiple pieces of information from my data set. This is going to just be so easy. I do a whole bunch of queries, right? Maybe I do the same query multiple times. Maybe I do different queries. Each one has some privacy budget, and I add them up. And you can see what happens, right? They can add up fast. So this is again the case where suppose all those F's are me asking that same question, trying to identify Tom in that data set. I add them all up so that I can get it. But at some point I hit the privacy budget and I can't ask any more questions because I've exceeded the privacy budget. All right. Another approach is parallel composition. This one's pretty neat. Parallel composition says I can take the data set, I can partition it. No information is given about the partition. I can choose whatever partition I want. I can divide it into everybody above age 40, everybody below age 40. I can divide it into states. I could slice it up however I want. Or I could even slice it up into individual rows. Okay? And I apply my epsilon differentially private mechanism to each subset. So I ask a question, and I'm able to ask the question of each block of my partition. And I'm able to get the result of asking the question of each block of my partition. And the new differentially private mechanism releases all that information to me. And that is an epsilon differentially private mechanism. It didn't add, right? And that kind of makes sense. It's a little bit, maybe it's a little counterintuitive, but if you think about it, right, the mechanism adds a certain amount of noise. Doesn't depend on the size of the data set. Depends on the sensitivity, and it depends on the privacy budget, but that's it. And so for a single line, it might add some noise. For 100 rows, it might add some noise. And so it works out that I'm able to then release the result for each block of my partition, and that's fine. It's still epsilon differentially private for me to do that. So for example, I compute the average for each state and report that average. That's epsilon differentially private. What if there's just one person in that state? Well, I add the same amount of noise I would add if there were 100 people or 1,000 people. And so I'm going to add quite a bit of noise for that one person compared to that one record. I'm going to add smaller relative noise, right, to that larger set of records for a different state. But it's going to wind up being epsilon differentially private. And that's kind of neat. Post-processing is very powerful. This says, give me a mechanism that's epsilon differentially private, that's M. Give me any deterministic or randomized function. Any function. So a deterministic function might be square root. So instead of computing trying to directly compute the standard deviation, I might compute the variance. And so, I compute the square of the maximum minus the minimum and divide it by n. And for the standard deviation, I just take the square root. And because my variance was epsilon differentially private, the square root of that is also epsilon differentially private. I can double it. I can divide it by a number. I can add a number to it. Whatever I do to it, it winds up still being epsilon differentially private. The privacy was baked in when it gave me the first answer. Anything I do to it after that preserves that privacy. Randomized function. What's a randomized function? Right? That's a function that adds potentially more noise or does something else to it. Right? So I could square it and add a random number to it. That's a randomized function. Any function. And there we go. So there's some homework. In the homework, you're going to do this. You're going to take some Python code, and you're going to write a program that takes some command line arguments. I'm going to give you a file name. I'm going to give you a zero-based integer index. That's going to be an index of a column in that file. So 0 is the first column, 1 is the second column, etc. I'm going to give you a lower bound and an upper bound. And you're going to then treat that file name as a CSV, or comma-separated value file. And here's again a place for you to use pandas. You can parse that CSV file yourself, but oh my word, does pandas make it easy, right? You just grab pandas, you import pandas, and then you say, read CSV, and you give it the file name, and it reads the CSV file, and now you have it in this nice set of structures. Okay, I gave you an example CSV file in ILO that you can play with. For the column given by the index, I want you to compute the epsilon differentially private average and standard deviation of the data in that column, selecting only records that are in the range given. So let's say I give you 0, 100. Then you are going to extract just the elements that are between 0 and 100 inclusive. And you will compute the average or the standard deviation, actually both, of those. And I want you to use epsilon of 0.2. And you'll print the computed average, a new line, and the standard deviation. So 2 numbers, 1 per line. Don't print anything else. I want to automatically check this. If you encounter an error, because I give you bad command line arguments, which I probably will, or I give you bad data, which I probably will, then I want you to trap that and print out something starting with error. Okay? Submit a zip or a TGZ file. Either one's fine. Don't submit something else. Don't find some crazy format and submit that. Give me something I can use. So you only need to pay attention to the specified index. If there's plenty of other stuff in there, don't worry about the other stuff. Just pull out the stuff that you're supposed to be looking at. If parsing the command line arguments is hard, you're doing something wrong. It should be easy to parse the command line arguments. And you should check them, right? This is a class about security, secure programming. Make your program handle its arguments in a robust way. Use Laplace noise. It says depending on the language, but that's from an old version where I let people use other languages. You're using Python, you're good. Okay? I've already given you a function that generates Laplace noise. For maximum and minimum, use the values provided on the command line. So I tell you 0 to 100, you'll just use those as the value. Now, my question for you, I want you to think about this. Play around with this and see what you get. Is that a good idea? Is it a good idea to let the analyst set the maximum and minimum from which you derive sensitivity? Does it matter? So play with that a little bit and see what you think. All right. And that's it.